In this video, we'll focus on the chemical shift. We noted already that the chemical shift is the x-axis of the spectrum. And the position of a peak on that x-axis, the chemical shift of a peak, is influenced by the chemical and magnetic environment of that proton. Remember that in NMR spectroscopy, we're applying a magnetic field to our sample in order to measure differences in nuclear spin states. Hydrogens in different environments will feel that magnetic field to different degrees. Hydrogens that feel less or very little of that magnetic field appear at lower chemical shifts, or to the right of our spectrum, and we say they're shielded from the magnetic field. And protons that feel much more of the magnetic field appear at higher chemical shift values on the left side of the spectrum, and we say they are de-shielded. Shielding occurs when protons are protected or blocked from feeling the external or applied magnetic field. And those protons are shielded by electrons, by electron density. Because of this, there are some key features of a structure that influence the chemical shift of a proton, and we'll look at the two most significant here. The first is nearby electronegative atoms, things like oxygen, nitrogen, and halogens. These atoms are electron withdrawing, they're electronegative, and they pull electron density towards themselves, and that in turn pulls electron density away from nearby hydrogens, and it allows the hydrogen to feel more of the applied magnetic field. As an example, we can compare methyl groups that are bound to different X groups. Here, X changes from fluorine to oxygen to chlorine to hydrogen to silicon. The electronegativity of that X atom decreases down the series. And what we see is that the chemical shift of the adjacent hydrogens also decreases. So as the electronegativity of the nearby atom decreases, the adjacent protons are more shielded and feel less of the applied magnetic field, and so they resonate at lower chemical shifts. The second structural feature that influences chemical shift is hybridization. As the S character of the carbon that a proton is attached to increases, the chemical shift of the proton increases. It becomes shifted downfield. And that's because those protons become de-shielded. If we think about the shapes of S and P orbitals, S orbitals are held closer to the nucleus. They hold the valence electrons more tightly than P orbitals. And when those electrons are held more tightly, the adjacent protons can feel more of the applied magnetic field. The second structural feature that influences chemical shift is hybridization. As the S character of the carbon that a proton is attached to increases, the chemical shift of the proton increases. It becomes shifted downfield. And that's because those protons become de-shielded. If we think about the shapes of S and P orbitals, S orbitals are closer to the nucleus. They hold the valence electrons more tightly than P orbitals. And when those electrons are held more tightly, the adjacent protons can feel more of the applied magnetic field. They are de-shielded and they shift downfield or to higher chemical shift values. Let's pause for a concept check. In each structure, compare the red and blue hydrogens and determine which will appear further downfield in the proton NMR spectrum. In the first molecule, the important difference between the red and blue hydrogens is how close they are to the oxygen atom. The oxygen is electronegative. It will pull electron density towards itself, and that will de-shield the neighboring protons. The closer the protons are to that oxygen, the more they will feel the influence of that oxygen, the more de-shielded they will be, and the further downfield they will appear. So in this first example, the red hydrogens that are closer to the oxygen will appear further downfield. In the second example, the difference between the red and blue hydrogens is the hybridization of the carbons that they're attached to. The blue hydrogen is on an sp2 hybridized carbon, while the red hydrogen is on an sp3 hybridized carbon. The increased S character of the sp2 hybridized carbon allows that blue proton to feel more of the applied magnetic field and leads to de-shielding of that proton. So here the blue proton will appear further downfield than the red protons. We'll end this lecture video with a compilation of some common NMR chemical shift ranges. And like IR spectroscopy, I want you to get comfortable with the ranges of chemical shifts for different types of protons, but then use the structural features of a molecule to understand and predict if a proton will be shifted toward the upfield or downfield end of that range. As an example, we discussed the effect of adjacent electronegative atoms on the chemical shift of nearby protons. For simple alkanes, structures without electronegative atoms, their protons appear very far upfield, around 1 ppm. As we introduce electronegative atoms, the nearby protons shift further downfield. These are structures containing groups like amines, carbonyls, nitro groups, oxygens. And what we can note is that the more electronegative the group is, the further downfield the protons are shifted. So an oxygen is more electronegative than a nitrogen, and the protons next to an oxygen are shifted down to about 4 ppm, while the protons next to a nitrogen are only shifted downfield to about 2 ppm. We also saw the influence of hybridization on the chemical shift. And here we can compare sp2 hybridized CH bonds to the sp3 hybridized CH bonds of alkanes. And the increased S character leads to a downfield shift of those protons, of alkenes and of arenes. The exception that you'll need to remember, and we'll discuss it in more detail later, is alkynes. Although they're sp hybridized, and we would predict them to resonate further downfield than alkenes or arenes, they actually appear around 2 ppm. And that's due to a competing effect, in this case of the internal magnetic field created by the pi bonds. It's something we call anisotropy. In all other cases, though, the electronegative atoms and S character of the carbon will lead to downfield shifted protons.